Good afternoon. This is the Bayesian machine learning class, and in particular the lecture on regression. I'm going to do a few, first some organizational announcements, and I'm going to share my screen with you. Let's see. Okay, so I hope you see my browser and you see the poll. Is that correct?
Yes, it is.
Okay, thanks. So we did a poll asking you guys how you were doing in the class, and well, I think this is a normal. It's not a Gaussian distribution, but it is a normal distribution. I mean, I've done these polls before, and this is all, what you usually expect after about halfway. And but I wanted to make an effort, particularly aimed at this third group. I'm a bit behind, feeling that I might get further behind. I think that's a sizable group, 14 people. Probably it's even larger, right? Only about half the people in the class voted. So I want to make an effort by after this regression class, we'll do an sort of like a catch-up Q&A session, and then I would hopefully one or a few of those 14 people are in the call, and we can go through some questions, and that may hopefully move you to the category just up there. If you are in this, if you voted I'm lost in this class, please let me know, right? Just send me a private message in Piazza. I mean, we're here to help you. The other thing I would like to pay attention to is we switched a class around. I also announced that in Piazza. As you know, the 24th of December was cancelled, and we moved the 24th to January 10th. As it was, we would have a probabilistic programming session on December 22nd, and B12 or B10 on latent variable models. We would have discussed it on January 10th, which would mean we would have to discuss three classes, B10, B11, and B12, all in 1 week. I think that's a bit much. I also think of everything that's coming up, B10 is the class with probably the some new material, and it's going to cost you the most time. So I want to schedule it actually, before the break. So you have, if you want, I mean, I want you to take your break, but at least I want you to be aware of that class, of that lecture before the break. So we moved it around. So we're going to have Friday classification, then next Wednesday latent variable models, and then we have a break. And on January 10th, we'll have a probabilistic programming session. And I believe, Wouter, you will also hand out the programming assignment. Is that correct?
Yeah.
Okay.
Well, so right after that session, I'll introduce the probabilistic programming assignment. Will become available. You can start working on it, and yep, I'll provide more information.
Super. So then you will have your assignment here, and yeah, I mean, I'm not sure what when do you know when the assignment will be due?
I think we settled on the 22nd of January, so that's still a week before the exam.
Okay.
So we'll make sure that everyone has plenty of time to both do the assignment and study for the exam.
Yeah. So then you'll have some time to do the assignment and still not have the assignment in your head when you start preparing for the written exam. Okay, so that's our plan. Now, then let's continue with this class regression. I think it's. I hope this should not be a difficult class in the sense that I hope that you recognize that again, this class is just a matter of applying our Bayesian machine learning recipe, right? Today we discuss curve fitting or regression, and Friday we discuss classification. I would say 90% of the successes of machine learning in industry is based on regression or classification, right? And 90% of that is probably based, at least for the complex problems, on deep learning, right? You have some curve fitting problem, and you pick a very big neural network with even more parameters and even more data, and then you train, and then you have a working algorithm. The remarkable, well, there are two remarkable things. One remarkable thing is that it technically works, that you can actually update millions of parameters by gradient descent, and that you get usually good outcome. The second remarkable thing is that how that 90% of interesting problems in some way can be reduced to either a regression or a classification problem. Right, and so for instance, speech recognition is a classification problem. Right, so and speech synthesis in a sense would be a regression problem. So that's why this class and also the next one are very important. In this class, we don't teach you how to apply deep neural net. We teach you that really regression and classification are also in principle Bayesian machine learning problems. It's just that the neural network literature hasn't completely caught up yet, right? But there is a lot of research going on in Bayesian deep learning, and so in the future, what shall we say, 5 years, maybe a bit more. I think most of deep learning will also be based on Bayesian methods. So by treating regression as a Bayesian method, what you'll see here, and we do it exactly according to our recipe, right? We first specify a model. That model we put in the form of a likelihood, and then we say, oh, I want to train these parameters on data, so I'm going to specify a prior. An inference, well, my posterior is just my prior times likelihood and then normalization. I hope you see my mouse, but so anyway, we carry that out. We chose a model and we chose a prior so that everything is Gaussian. So blah blah blah. You can apply your Gaussian multiplication formulas, and you have an answer. And that's the proper answer. That's just all there is to regression, really. The interesting thing is that if you then apply this to, let's say, making a prediction for a new data point, say, okay, now I have a new data point, x bullet, xn plus 1 has been observed. What is the probability distribution for y bullet, for, let's say, my output, given the data? I'm not interested in the parameters. I just given my data set and my model assumptions, right? I should say here, comma m. I have model assumptions. I have a bunch of data. I have a new data point. What is the probability distribution of y dot? Well, just apply marginalization here, the Gaussian update formulas, and something comes out. And the interesting thing that comes out is, so even though you have some input and it's just a number, right? It's just or a factor of a number. The output is actually a distribution, right? There's uncertainty about the output, and it totally makes sense because, well, we assumed that there was some uncertainty in how the input maps to the output by beta, right? This beta describes here, well, here, right? Here. Beta describes the uncertainty in the map from inputs to the outputs. So that you should also see that here. And well, if we learn there's also uncertainty about the weights are. And if we learn from some finite set of observations, we're not going to have an infinite precision for the weights. So there is also some uncertainty about the output due to uncertainty about the weights, which is due to the fact that, well, we have a prior distribution, right? And we have a finite set of data and not an infinite set of data. And so you don't have to be smart about this in order to get this answer. You just have to know your Bayesian update rules, and you have to be aware of how to execute these update rules when there are Gaussians in there. And that's all. And that's really the whole story about Bayesian regression. And you can apply this to simple models here. You can also apply it to deep neural networks and set priors on weights in your deep neural networks, and you would get similar expressions. Now, of course, if your deep neural network is a nonlinear network, then if you push Gaussians through a nonlinear network, you don't get Gaussians at the output. So you may have numerical issues, or you may have some computational problem, but it doesn't change the recipe, right? So Bayesian neural networks and deep neural networks in a Bayesian way, the only issue there why you don't see it more often is a computational thing, right? This integration may be difficult to compute, but eventually, the numerical recipes for computing these integrals are going to be so good that that's going to be the method of choice. And we do an example, and so, for instance, here, I think this is a nice graph. There is an underlying process which is the green one, some sinusoid, and then we make noisy observations here. When we make one observation here, the blue dot, and then we just draw from the posterior weights and just plot curves with drawings from the posterior weights, and you see, well, I mean, most of the graphs are, let's say, in the neighborhood of this point, but otherwise it could be almost anything. With 2 data points, it's like this. And if you have a lot of data points, there's still a lot of possible functions, but they all kind of look Gaussian, right? So as you get more data points, your probability distribution, or let's say the possible underlying functions, more and more are going to look like the green one. Now, then there is a small section on comparing this to least squares, because what are you used to? You're used to basically this formula, right? You say I have some function, linear function here, and I have some given outputs, and how do I get my weights in curve fitting? Well, I minimize the sum of squared errors. There's nothing wrong with that, right? That works. You can compute your gradient of the sum of squared errors and set the gradient to 0, and you get your answer for your weights. It turns out that least square solution happens to be the same to the maximum likelihood solution for the model that we used. But the difference is that in least squares, you basically you don't have underlying assumptions, at least they are not very explicit, right? We got the maximum likelihood answer here. We got this answer by making some model assumptions, right? In particular, we made a model assumption that the noise in the observations is Gaussian distributed. And not only that, it's for each observation n, the variance is not a function of n, right? So it's independently and identically distributed. So if I would have any different with these assumptions, yes, then maximum likelihood becomes least squares. But I may have some extra knowledge about my problem, which makes these assumptions not very reasonable. And so that's what we then do in let's say in the next cell, or not. This this is a different example, but in this cell where we say, so what now? Or actually, it is, I think, this cell. What now if we assume that the variance of the measurement error varies with the sampling index, right? So En now is a Gaussian zero mean with a variance that depends on n. You could assume that. Okay, what is then is still least square the best algorithm? No, it's not. That's not right. But as a Bayesian, you don't care. You just write down your likelihood function. You write down your prior. You compute your posterior. You get an answer. And if you then would say, now, if I would assume that my prior would be uniform by setting alpha to 0, what would the weights be? What is my maximum likelihood? Answer. You get this expression for the maximum likelihood weights. Right? Notice that this is just a vector because everything in X here are just numbers, are observations. Lambdas are weights that are given, and Y are also is also from your data set. So this just evaluates to a vector. This is called the weighted least square solution. By deriving it through the Bayesian way, we don't care what it's called. You just get your answer, right? And the answer is what it is. And you don't need to make up a new algorithm for every type of assumption that you have. You make your assumptions in your model, and then you do the same recipe. You just do inference, and and you always do inference in the same way. And whatever comes out, and that's the correct solution. And other people may call it weighted least square or iteratively weighted least square or whatever they call it. That's just in a way irrelevant if the answer is correct, right? So to me, that's the whole class. There's an example, but that's the summary of the class. I'm going to turn off the screen. Maybe you have questions and I may want to turn on the screen again, but I want to turn it to you now. If you have any questions, please raise your hand or say something in the chat. Yeah, Sveta.
Yeah, hi. When we are choosing the prior for the weights, we are assuming it to be Gaussian distributed. Is it again because the Gaussian distribution gives us the least amount of assumption we can have about the weights? And is that why we choose it to be the prior?
Yeah. I would say. I mean, there's actually a question in the exercises session. I mean, well, first I should say you can choose any prior that you want. If you have some additional information, if you have, let's say, observed another data set and you train on that data set first and you get some posterior from that data set, you can choose that posterior as your new prior for, let's say, for this data set, right? So wherever you get your information from, your goal is to in some way summarize that information in your prior. The Bayesian approach, you can think of it, well, that's kind of a nuisance that I have to always choose a prior. On the other hand, and the real way of the proper way of looking at it is the honest way, namely if you do machine learning, you must make model assumptions. You can push it under the rug as we do with least squares, or you can be explicit about it and honest about it. And so the Bayesian approach is just open about it, and you are forced to make an assumption on your distribution. If you say no, I don't want to do it, I want to do maximum likelihood, basically you make a uniform assumption. The Gaussian assumption has a couple of nice advantages that we discussed in the Gaussian lecture. It's computationally very nice. if the likelihood happens to be Gaussian, because then they are conjugate pairs, and I can analytically compute the answer. The other thing is that indeed, for other distributions with the same kind of variance, the Gaussian has the maximum entropy, which is a way of saying it makes the least amount of additional assumptions given the variance, right? You have no additional assumptions. Why would you make any additional assumptions that you don't have? So both computationally and from an information theoretic viewpoint, it's a nice distribution to choose. The other thing is that if let's say if your data would come in sequentially, right? So and you would compute a posterior, and so you start with a prior, and then you multiply with the likelihood, and then okay, you get a posterior, but you get a new data point, so you multiply with a likelihood, and you get a posterior, and you multiply with a new likelihood. So the posterior would be a prior times a likelihood for data point 1 times a likelihood for data point 2 times a likelihood. So you get this whole multiplication of likelihood times likelihood. And we also saw in the Gaussian class, we didn't prove it, but any function with a single peak, if you multiply, if you raise it to higher and higher powers, it becomes a Gaussian. So you might as well start with a Gaussian because technically it will end up being a Gaussian in the end for a very large range of likelihoods. So they're both, let's say, information theoretic reasons as also computational reasons why it's convenient and good to choose a Gaussian. And the other thing is that, yeah, I wanted to choose an example here that has an analytical answer. But if you have other sources of information, you don't have to choose a Gaussian, right?
Right. So then my question is, okay, I do choose it to be Gaussian distributed. It didn't strike me, but then while doing the exercise, it said that, okay, take it as it's a full matrix. The variance is a full matrix. So my question now is, okay, why do we assume it to be a diagonal matrix as a covariance matrix when assumed to be prior?
It's sort of the same answer. I mean, I don't want to prescribe you to do anything. I could have done this exact, let's say.
Is it?
I'm gonna share my screen and then point it out. Okay. So the prior shows up here, right? In your the prior doesn't show up here, but it shows up here. And if you would have chosen another Gaussian prior, you would have seen it here. You would have seen your sigma prior. So it's up to you. I mean, but I had to choose something, and for me, let's say I took this the standpoint here, like, okay, I really don't know anything. I just need to. I must make a I must have some prior assumption. I don't know much about this problem. So what is the simplest I can think of? Well, give the individual coefficients some variance or some precision alpha, and that's it. I don't want to make any other assumptions. And then but if you feel like you want to, let's say you want to do here instead of alpha -1, if you want to do here some sigma, it's also fine. It's just going to show up here as sigma. It's not going to be a big deal. But then if you do that, I will I will counter the question, and I may ask you, so what makes you think, okay, let's say you would choose, how would you choose that sigma, right? I mean, how would you choose the entries? You have to assign a value, right? And so I would ask you, okay, how do you come up with the values for that? So it for simplicity's sake, we just use one parameter alpha here. And then if I have quite a lot of parameters, it doesn't really matter, right? This alpha will just, the prior will just disappear, and the likelihood and the data will start to dominate. Does that answer your question?
Yes, yes, yes. So under the maximum likelihood estimation for linear regression model, there was a note where if the number of training samples are lesser than the input parameters, then x transpose x will not be invertible. I get like why. Okay, if we would want the number of training samples to be at least as much as the input parameters, because then we won't have enough number of equations to get a solution. Um, uh, but I'm not able to really understand why x transpose x will not be invertible.
Okay. So yeah, I'll
And
go.
yeah, a
Okay.
follow-up is why does a Bayesian solution does not suffer from this issue? That was
Yeah.
both.
Okay.
Yeah.
Okay. So here is the Bayesian solution for the posterior for the weights, right? And now let's just say that you have that you do filtering. It means you get one data point at a time. So you are at time n, and you get one data point at n+1, and you want to update your weights, and then you get one data point, and you want to update your weights. So in this case, the number of observations is 1, and x may be, I don't know, 10-dimensional or 100-dimensional, but then this matrix would be, let's say, if it's 10-dimensional, would be 10 by 10, but it's only based on one data point. So it's highly degenerate. There is not enough degrees of freedom in it, and it's not invertible. The determinant will be 0. And so x prime or x transpose times x will not be invertible in that case. Now in the Bayesian approach, that's okay, because alpha times I plus beta times whatever this matrix is still invertible, because of alpha times I have some number on the diagonals, right? So the determinant will not be 0, and so this is going to be invertible in the Bayesian case, no matter how many observations I have. However, if I would do maximum likelihood estimation or least squares, then this alpha term disappears, and then I would have to invert this matrix, and that's, I mean, if I have less observations than this dimension of x, then this matrix is not invertible, and then the whole thing will blow up. So the Bayesian approach will not blow up, but maximum likelihood will blow up, and the reason is, well, because you didn't assign a prior. By not assigning a prior, you are basically saying W can be anything, right? There's no constraints. Then you give a little bit of data, not enough, and the maximum likelihood is just not able to, it's not enough information to say anything interesting about the weights, because your search space is just too big. But by constraining what W can be by giving a prior, and particularly by giving a prior like this, you make sure that even if I have one more data point, I can do a new update. Right, the Bayesian update will always work. I'm not sure if I'm clear about that. So particularly for filtering, and let's say the entire recursive least squares algorithm is based on this idea, right? Recursive least square is a filtering algorithm for doing just least squares, right? For just minimizing the sum of minimizing the sum of squared errors, but you want to do it with one data point at a time. And if you do it with one data point at a time, this matrix X transpose times X is not invertible. So if you wouldn't have a particular algorithm recursively squares, then will not work. So recursively squares is an algorithm where you can actually it's constructed in such a way that you can do the inverse. And actually, recursively squares comes out to be basically the same thing as what we derive here. You also have an extra term here. So in a sense, we've also derived recursively squares here. Is that clear, or do you need?
Well, I now get why the Bayesian solution does not suffer from the issue of number of training samples being fewer, but I'm still not able to get how do I mathematically prove that X transpose X will be not invertible if n is less than m, because X transpose X is an m by m matrix, right?
It's a degenerate, because I mean then let's say then this xt, yeah, the way it's constructed is just a column, right? It's just, let's say it's just this thing here, the first observation, and there is no second observation, right? So and n is just one, so it's just a vector, and so am I right here? Or no, I should say it's a row vector then. If I have one observation, then the matrix A is just a row vector, right?
Yeah.
Because n is 1 here, so I have a 1 times m. So this guy here will be a row vector, will be a column vector times a row vector. Yeah, that will give you a matrix that has determinant 0. So that's
okay. Yeah.
Yeah, so that's not invertible. But if I add at every, if I take that matrix and I add at every diagonal, every entry on the diagonal, I add the value alpha divided by beta, with alpha and beta both just, let's say, positive numbers. And it's a small number because alpha is going to be very small. At least you can choose alpha to be very small. Then it's invertible, and yeah, alpha plays the role again as a prior, but it plays a similar role as, let's say, pseudo observations. You know.
Yes, now I understand. Thank you.
Okay, cool. Any other questions about regression? Class? Okay, I see something in the chat. Oh boy, there's a. Oh, it's Doctor who says something. Yeah.
I added to your comment on.
Okay, could you please explain what basis function and how you choose them? Okay. Again, I'm going to share my screen. Now, the example we do here is very simple, right? We build a map from X to Y. Let's say this here, yn is some function of X, and that function has parameters, and that function may not be a perfect representation of how X maps to Y, and whatever we don't get perfect about it, we capture in the noise. That map doesn't have to be a linear map, right? So what we do here is we say, okay, so I still would like to get an expression that's going to be linear with respect to the parameters, but perhaps non-linear with respect to xn. I want to build a non-linear map from x to y. And this is such a map, right? This is a map that, phi j is some function of xn. And I have these things I call, basis functions is what they are called. This allows me to build a nonlinear map, a nonlinear function from x to y, but this function is still linear with respect to w, and so that makes it easy to adapt with respect to w, and still we can build a complex function. Then the question is, okay, how do you choose them? Well, you choose, there aren't, I mean, maybe there is actually a mathematical theory about it, but say in machine learning, what people often do is they just choose them to be Gaussians that are shifted versions of each other. Right, so here's a plot of these. I have 9 basis functions. The green one here is the first one, and then this one is the second one, and so forth. Right, so these are actually, so this is one, and here's the red one. Right, so here are 9 basis functions. They're basically Gaussians that are shifted, or are they Gaussians? Yeah. And that's a very common way of doing it. Please remember, no, you don't remember that, but because it's going to be in a future class, in the latent variable class, we're going to discuss something called a Gaussian mixture model. And you can kind of imagine what it is. This is sort of a Gaussian mixture model. This is a Gaussian function, right? And the function, and this Gaussian can have different. Each Gaussian can have a different variance and a different location. So where the peak is. And then I have a mixture coefficients W, and then I sum them, and I get my my output function. It turns out that you can build any function with that as long as you have enough Gaussians. So it's always nice, just like a neural net, that you come up with a model that with which you can build, let's say, a really wide range of functions, right? Well, if you choose Gaussians and you weigh them and you have as parameters the location, the peak of the Gaussian, and the width, then you can build any function. You can see that here, that if I make only one observation, like x1 and y1, and I'm going to try to come up with posterior for the weights, and then I just pull from that weight, just pull samples from the distribution, and then I show this function. You see, these functions are completely wild. It can be almost anything. Right? This is here goes one. I should have given them different colors, right? But the other ones are completely different, right? I can make almost any function with this recipe. Only once I've observed a lot of data, all these functions kind of turn into sinusoids. So you don't have to choose a Gaussian. There are I think splines and other kinds of functions, sigmoids, and in neural nets they use sigmoids, right? And there's other kinds of functions you can use. But yeah, the Gaussian is a good choice. But we could have done, you could also have tried triangles or whatever. The whole point was to build a nonlinear function from x to y and still have that's still linear in W. Is that clear? Okay. then let's see. Yeah.
Could you go back to the plots and explain those plots once more?
Yeah, sure. I'll be happy to. These plots or the plots above?
Actually, both.
Okay, both. Okay, so we have a model assumption, right? And I start out with no data, so just my model assumption. So I have no likelihood because I have no data point, and I start with my prior, which is Gaussian, with the mean at 0, 0 here, and there's a variance, right? That's 1 over alpha, and this is a heat map, right? You can kind of see that, okay, this is, if you look from above, and this looks like a Gaussian. Would you agree with that? And then I just pick a point. We sample. I just pick a point from this, and then I draw the line that corresponds to that. It's the line y equals w times x, as this line. And I pick another point from this, let's say from another point. I just sample from the distribution, right? I just sample from this distribution. Another point, let's say here, and I get this line. And I pick another point here, and I get this line. And then we say, so basically by setting up a prior, we have said these functions here on the right. These are all possible functions. I mean, they look all different, but yeah, I haven't seen any data yet, so it's normal that they all look different. But now I observe a data point here, the blue point. And with the blue point, I can fill that in my my model and come up with a likelihood function. Here's the likelihood function for this model. And I multiply this likelihood now with the prior here. So I multiply this guy with this function, and this comes out, right? You can kind of agree that, if I multiply this by this, that this comes out. And now if I just sample from this distribution a W and I plot the graph, then I may get this one. And I sample another point from this distribution and I plot the graph and I get this one. And I sample another one and I get this one. So now you see they're already closer. I mean, all the graphs look still very wild, but they are quite close to the data point. This data point helps to constrain the different kinds of models, really. And I make another assumption, another observation, this assumption here. Sorry, this observation. So I write down the likelihood and I multiply this prior, and now I get this posterior. By the way, the white cross means how the data was generated. Right? That's the real value of W, but we don't know that, right? The model says after I've observed the blue point and these two blue points, the model says this is my posterior. Now I can start sampling from this posterior and I get all these lines as possible functions. I can keep going, right? I keep going. And after observing these data points, my posterior has nearly all its probability mass close to where the real W or the real value of W is. So if I keep sampling from this probability distribution, all my W's will be about the same value. And so all my lines will be about the same. So all my lines are now here. That's the whole process of point by point here, like step by step, data point by data point of doing Bayesian inference. You move from a prior, and by a prior, you can also draw your functions then the only thing that collecting data does is just constrain basically the space of functions from being very wild to, you know, concentrated around the data points. And then here it's they all look like lines. Now, in the other, yes.
Yes. So when you say you're sampling the W's from the posterior, which gets updated as we observe the data point, with each update, the values of the W's, when I randomly pick from the distribution, they'll tend to be very close to each other. That's how I should be interpreting the.
Yeah, you don't just sample, let's say, randomly from the square. You sample from the probability distribution
Yes.
that I drew here. And that means that in this case, nearly all probability mass, if you will, is concentrated around here. And in this case, I mean, the samples I pick will be all over the place, right?
Yeah.
Yeah,
So
and
then,
here,
yeah. Yeah. So then, can I say that we want the variance to reduce and have like a very sharp distribution with the update? Is that how we can like quantify it?
yeah. So I mean, but it's in a way. I mean, you're right. But I wouldn't even say we wanted to reduce. It just happens to reduce if you make more observations, right? All we do is carry out, let's say, Bayesian updating. You have to start somewhere, so you say where you start, and all we do is if I make an observation, I construct a likelihood, I multiply with the prior, I get a posterior, and I keep doing that. Multiply with this likelihood, get this posterior, multiply with this likelihood, get this posterior, and so forth. And another way of visualizing this, you can visualize it here in the weight space, and indeed you see that the variance keeps decreasing. Yes, absolutely. And as a result of that, if you keep picking W's from the probability distribution, yeah, then these lines will get closer and closer together. There's no other way, right? They will never, I mean, unless you have a infinite amount of data, these lines will never completely overlap.
Right. So then finally, when I say that, okay, this is after doing the posterior update and let's say after some iteration, how I can just choose any of the W's, or can I average it out? I think we touched upon.
Yeah. So let's say that you are now in this situation. So you've observed all these blue data points here, right? And say, okay, and so now the question may be, what, I mean, it's not drawn in here, but what if I assume a new X somewhere, let's say very close to -1, let's say here, I observe a new X value, I have no data point there. So not in the training data set. So the question may be, make a prediction for Y. What is Y if I observe X here close to -1, let's say -0.9 or something, no data point. Well, there's two ways. You could just say, I just pick a value of W by sampling from here, which is right, and then I compute W times X, and that will give me a value for Y, and that's fine. But let's say the Bayesian approach would say you basically want to average out over all possible values of W, and you want to weigh by the posterior probability for W. And that means technically you're going to kind of weigh out all the possible functions here. And so you're going to get a posterior distribution for Y. You're now going to get some uncertainty for Y because you're not sure if if W is this point or this point or this point or this point or this point, right?
Right. Okay. So that's why we have the marginalization across all W's. That's what we
Yeah.
predict. Okay. Okay.
Yeah. So marginalization is the proper Bayesian approach, because what marginalization does, let's say what we do here, this is the proper Bayesian approach, right? We say, okay, we have this data generating distribution for a given W and a given observations X bullet. This is how Y bullet is distributed. And you have given that model, right? We have specified that model. PWD is our posterior. That's exactly this thing right here. And yeah, what this formula does is just, it says, basically it's going to weigh all these data generating distributions with the possible values of W. I'm integrating W out of here, right? Going from here to this formula is just a Bayesian computation. It's just marginalization. There's nothing, you can't argue with it, right? It's just how probability theory works. Now, what you can do is you say, I don't know how to do this computation. All these Gaussians is too difficult. You know what? I'm just going to sample from here. Basically, what you're saying is this posterior probability over W given D, I'm going to approximate that now with a delta distribution. And okay, if I have the integral of P Y bullet given X bullet given W times some delta distribution over W, well, then the answer of this integral is going to be P Y bullet given X bullet, and then I just plug in the value of well, where that delta distribution is located. So that makes the computation a lot simpler. I don't have to do this or multiply these Gaussians. But you're making an error, right? Because here we have a Gaussian posterior, and now you're saying, no, I'm going to replace that with a delta distribution. So from a Bayesian viewpoint, just picking a weight from this distribution and then computing with that, that's not entirely correct. I mean, it's computationally simpler, and that's why in practice, you know, if this posterior is really concentrated, right? It may just be fine, right? It may solve your problem. So why bother? Everything fine. From an engineering viewpoint, no problem. But technically speaking, the proper way is to not pick from this distribution, but to actually plug in, marginalize the weights out of it, because you don't care about the weights. You care, the only things that are given is a data set, a model specification. I should have said here, comma M, your model specification, and X bullet. Those are the things you have in your hands. And everything else you don't have in your hands, right? W is just some internal variable of your model, and you don't care about it. So integrate it out. That's how you. So the answer then, the answer's here. Whatever the answer is, it will not contain W. It will contain only things that you have in your hands, like beta you specified, X bullet was given to you, SN. Well, we have to go upstairs to find what SN was here, but SN, alpha and beta, you specified. X is your training data set. So this is also all given to you. So, you know, the answer will be some probability, some Gaussian probability distribution, and everything is going to be in the parameters of that distribution. This distribution is a distribution over Y bullet, and it has a particular mean value and a particular variance. But this mean and this variance is composed of all the data, right? All the entire training set, and also X bullet is in there, and it won't have anything else. It will just have all your observations. And also your, let's say, your prior assumptions, alpha and beta. your model assumptions, and it won't have anything else. And it just, in a sense, it rolls out, right? You don't have to do anything. You just, you have to compute these integrals, of course, but you don't have to come up with an algorithm. It's probability theory is your algorithm. Okay.
Yes.
Good question, and thank you for asking these questions, because it allows me to, yeah, to explain it a bit more, and I think it also helps other people.
Yeah, and these graphs as well. If you could also go.
Yeah, so this is the same graph, but now we are talking about not a straight line. So what we do here, let's first go to this, because this is kind of similar to the graph above. In the graph that we just talked through, our model was W, or inner product of W and X. So it could only make lines. So when I would pick a value for W from the posterior distribution, and I would just, let's say, plot the function that would imply, it would be a line. But here, our model is, this is our model, right? So if I pick a value for W, I have some nonlinear function of X. Because, yeah, I mean, phi of M are these 9 Gaussians. And they're going to have, you know, I'm going to weigh each of them differently. Right, so I'm going to get wild functions. And indeed, in the beginning, with one data point, all these functions are just wild. They don't look at all like where the data comes from. The data comes from the green curve with a bit of noise. And in the same way as before, as I just, like this is an interesting graph here. You see that in the neighborhood of where I have my data points, and I mean in the neighborhood around the same values of X. So around here I have a data point. The variance of Y is not very big. Here, the variance of Y, I mean, so the model can predict quite well where Y is going to be if for data points that are close to, yeah, my observations. But here I have no data points. So the possibilities for the functions vary wildly, and here also it very wildly. But where I have data points, the variance for Y is going to be a bit smaller. I can predict the function a little better there, and eventually with lots of data points. This is just like a sample of, or a set of possible functions, right? That were generated by sampling W from my posterior distribution and then plotting this function. Right, and then here we do kind of the same thing, but now we also plot this the uncertainty. And so here you see, let's say here we basically say, well, if I would just plot the mean value and for one function and the uncertainty after pulling, now I have one data point, right, and I pick one W. And then I plot the mean and the variance of that function. Then it looks like this. So here's the mean, it goes through this point. And here you see that the mean again goes through 2 points. Here it goes through these points. But the variance of the function, because the function is going to have a variance, I have a posterior over W, and that introduces uncertainty here. And I also have uncertainty here. And so the variance is bigger where I don't have training data. Here I have training data, so the variance is not very big. But here I don't have training data, so I have a big variance still lots of uncertainty. I haven't seen any data points, so what do I know, right? But here I've seen a data point. If I get lots of data points, then yeah, the mean is very close. there's still always some remaining uncertainty I will never get rid of, because I have in my model y is w times a bunch of functions of xn, but so there's uncertainty about w that will lead to uncertainty. But if that disappears, there's still a Gaussian with variance beta -1, and that beta -1 is really the width of this cylinder here. So even if I get like, I don't know, 1 million more data points, I will still see this cylinder here. And there will be almost no uncertainty about w. So this will look like a nice sinusoidal form that will be very, very close to the green one. And then I will still have this this cylinder around it due to this term.
So I have a question. I get the plots on the lower one where we have the different basis function and its corresponding weight, and how it's getting changed with each data point. Yeah. So the ones above which has a shaded region, like, is it a region because we have the noise, which is uh, a continuous distribution? What am I missing in interpreting the why?
Yeah, you're getting the, let's say, the predictive distribution. This is a Gaussian, right? We've established here that the posterior for y for any given input is going to be a Gaussian with some mean and some variance. So that means that for any given value of x, there's going to be a mean value for y here and some variance. And that's also true for this value of x. There's going to be a mean value and some variance for y. And what we plot here is for each value of x, the predicted, let's say the mean value of y and the variance. And it turns out, and it makes sense, that near the points where you have observations, your uncertainty about y is going to be less than in areas where you have no observations. So you can, if you would just, you see that variance is really the thickness of, let's say, the pink shape in the y direction.
Right. Okay. And the plots below, those are the 9 basis function and its corresponding weight, which gets updated with.
These are the 9. This is number 1, the green one, and the blue one is number 2, and the here whatever is sort of like light brownish one is number 3.
Yes. So the 4 plots below this one, figure 3.9.
This one?
Yeah. This one is just W transpose phi of x. So it's the basis function with its corresponding weight as it gets updated. So this does
no. This is okay. Some plots of draws of posterior for the functions. So what happened here is, well, after each observation, here's 1 observation, 2 observations, 4 observations. We build a posterior for W again, and then we make a draw from that posterior for W, and then that particular W, we plot this function. This is just so for W, I'm going to have a value, and that value is drawn from the posterior, and I do that 5 times, and then I get 5 curves.
Okay, this is same as the previous one, right? Where we had a couple of lines that kept changing.
Yeah, I mean, you can, you can see, if in one way you can you see that this plot right here, these are sort of these red curves, are sort of random curves drawn out of the pink area.
Okay.
And here, let's say, and here actually for all four, right? So these curves here, they all look like sinusoids, are random curves drawn from this cylinder here. And the same here and here. I mean, that's not exactly true, the way I say it, but it's a nice way of looking at it, right? I mean, that.
You, maybe to add to that, you draw a coefficient from the posterior distribution over coefficients, in this case weights, W, and each value for the weights generates a curve, like one of the red curves below that. It generates a curve of a certain, that moves in a certain place, a very specific curve.
Yeah, but in this case, we didn't draw the posterior. In this example, there's a posterior, right? Here we can actually say I make draws from this distribution. I draw from this distribution, and that gives me a curve. And I draw another one, and it gives me another curve. Here we do the same thing, different curves, but there is no plot of the posteriors. This here is not a plot of the posteriors over the weights.
Oh, yeah, got it, yeah.
Right, all right, so we missed here the posterior over the weights, but I mean, you can kind of imagine it's the same process. And let's say the phenomenon that you see here played out is exactly the same phenomenon that you see played out here. Just here it is, for simplicity, just let's say, just lines. A model assumption was a line. And so the lines get closer and closer together. And here we had a nonlinear function, right? We had a bunch of basis functions over xn, linear in W. Okay, so some kind of what we call a mixture model. Can be a very complex function, a nonlinear function, and that's what you see here. But it's the same idea. Over time, these wildly convoluted curves all become sinusoids.
Right. Sorry, I was working on something and I zoned out for a bit. I didn't realize we were looking at the predictive. Yeah. All right.
Yeah. Okay. So it's like we have the posterior distribution, and I pick some samples of W, and then I get the distribution for Y, and the distributions for Y is for those samples are the red curves, and obviously they're going to belong to the pink region because they're still we've still taken samples from the posterior for W, and if you make the prediction for Y, it has to belong to the pink region, right?
Yep.
Yeah. Okay. One more question is regarding the basis function. So you did touch upon like how these basis functions are chosen. I also want to know if they have to have some like orthogonality conditions to be met, some linear independence to be met.
No, they don't. I mean, it will be nice to have some of those. I mean, there's a whole, I think, field of mathematics called approximation theory that that works on how to choose good basis functions, right? And but we don't make any assumptions here. We just choose them as an example. In machine learning, it's common. I think in machine learning we call them radial basis functions, but it doesn't really matter. It's just Gaussians that are shifted, and I'm sure there are some nice properties about them, but we didn't need any of these properties here, right?
I can try and add something to that again. So there's this wonderful property that, so if you're familiar with polynomials, right, Sveta?
Yes.
So a polynomial is able to, if you're familiar also with Taylor's theorem, a polynomial is able to approximate a function, and the more terms you add, so the higher order the polynomial, the better it is able to approximate that function. And there's this, so this is not, so there's this theorem, or this entire subfield of machine learning that revolves around something called kernels. But in that case, you would take two basis functions, and you take their inner product to generate a kernel. It's not what we describe here. Let's not go too much into it. But if you take the inner product of two infinite order polynomials, you'll get something called the radial basis function, which is described as shown here on the lecture, this e to the power of x, and then shifted and scaled. So there's a deep mathematical connection to infinite order polynomials and their power to approximate functions.
Right.
But it's a bit yeah. Here we're just using a finite order basis function. We're not going into kernels and everything.
Right. Okay. Yeah. Thanks.
Okay.
Yeah.
Anybody else a question on regression? So I suggest, because we are well over an hour into it, I'm going to stop the recording. Let me just stop the recording. So thank you for this class. Stop the recording.